In this video, we're going to look at solving systems of equations that involve nonlinear functions. So I'm going to ask you to recall that in the previous courses, you've solved systems of equations that involved just straight lines, and the concept is essentially the same here. So we have multiple equations representing functions, and the solution to the system represents any and all coordinates of points that satisfy all of the functions. In other words, points that are on all of them, points of intersection. And we can use similar strategies to what we used for linear functions. So substitution and elimination being the primary ones. So if we look at this first system here, we have a linear equation, y equals 2x minus 5. And we also have a nonlinear, y equals x squared minus 4x. And since we know that y has to equal y in these two equations, that has to be the same y value, we can conclude that 2x minus 5, which is equal to y, and x squared minus 4x, which is also equal to y, have to be equal to each other. This gives us a quadratic equation, so we can move everything over to the right-hand side. We have x squared minus 6x plus 5, and that is factorable. So it gives us factors of x minus 5 and x minus 1, which tells me that in order for this equation to be true, x has to equal 5 or x has to equal 1. Now that's not the end of our problem because we had y and x. We're in fact looking for coordinates of points. So I have to figure out what y value corresponds to each of these x values. And for that, I can substitute into either one of the two original equations. It's a little easier with the first one. So 2 times 5 minus 5 is 5. But I would have gotten the same thing had I done 5 squared minus 4 times 5. That is also 5. And if I substitute x equals 1, 2 times 1 minus 5 gives me negative 3. Or if I wanted 1 squared minus 4 is also negative 3. So that means that the two solutions to this system of equations are the point 5, 5 and the point 1, negative 3. Those are the 2 points of intersection. From a graphical perspective, I can look at the line and the parabola and see that they do in fact intersect in these two coordinates. So that's a good way to check your work, or in any case where you're not asked to solve it algebraically, just to graph and find intersections right from the start. Let's look at a couple more examples, but that is the same basic principle. So here we have another linear and parabola. So if I start with the same principle that y has to equal y, I end up seeing that 2x minus 3 therefore has to equal 2x squared plus 3x plus 9. When I move everything over to the one side, 0 equals 2x squared plus x plus 12. And when I think about how to solve this one, there aren't any factors that have a product of 24 and a sum of 1. So I'm going to go to the quadratic formula. X equals negative b, which is negative 1, plus or minus the square root of b squared, which is 1, minus 4 times 2 times 12. So 4 times 2 is 8, times 12 is 96, divided by 2 times 2, so divided by 4. Now I see the problem because inside of this square root, so the discriminant is a negative value, which means that this has no solutions. From a graphical standpoint, what that means is that these two functions, the y equals 2x minus 1 and the y equals 2x squared plus 3x plus 9, don't intersect. And I can verify that by looking at the graph. And sure enough, there's no way these will ever cross. So no solutions shows up as a potential situation. All right, let's look at one where we don't have linear and linear, we actually have two parabolas. But that doesn't change how I approach the problem because I know that y equals y. I know that 6x squared plus 7x minus 4 has to be equal to 2x squared minus x plus 1. Quadratic equation, combine like terms, I get 4x squared plus 8x minus 5 equals 0. And this one is factorable. So I'm looking for two numbers that have a product of minus 20 and a sum of 8. So that's 10 and negative 2. So that's going to be 2x and 2x. And that one's going to be positive, that one's going to be negative, which means that my x values would have to be negative 5 over 2 or 1/2. Now, it's sort of equivalent here whether I substitute those into the first equation or the second equation. But when I substitute into the first equation or the second equation, either one of them, the first value, -5/2, I get y equals 16. And when I substitute in x equals 1/2, I get y equals 1, which means that the two intersection points in this case would be the point -5/2, 16, and the point 1/2, 1. And we can, in fact, graphically verify and just sort of see what's going on with these two parabolas. We see that those are, in fact, the points of intersection. Now, with two parabolas, like with a line and a parabola, it's possible to have two intersections. That's mostly what you'll see. It's also possible to have no intersections. So I can think about if I had a parabola that was going up like this, for example, and a parabola that was going down like that, they would never intersect. It's also possible to have just a single intersection, either for lines or two parabolas. So if I have, for example, a parabola and then maybe a line that just skips across at a point of tangency, I might have just one solution. Or the same thing could happen with two different parabolas. I could have just a single intersection at a point of tangency. So you can see 0, 1, or 2 intersections with these sorts of systems. Now let's look at a system that doesn't actually involve two functions at all. It involves a function and a relation. The first one here, x squared plus y squared equals 25, actually represents a circle. And then x minus y equals 1 does represent a straight line. But the issue here is that I can't just do what I did before, where I say, well, y equals y. I mean, I could, it's messier and it involves some potential extraneous roots. And the reason for that is that in order to isolate y in that first equation, I get y squared equals 25 minus x squared. But when I take the square root, I have to remember that that's a positive or a negative. So this system of two equations has now become a system of three equations. Y equals positive square root of 25 minus x squared. Y equals negative square root of 25 minus x squared. And y equals x minus 1 is what I would get in the second equation if I isolated y. So if I want to solve this on a graphing calculator, I have to graph all three of those equations and find intersections. And it's just messier, and I don't have to do that because I can use substitution. If I take that second equation and isolate either x or y, doesn't matter which, I'm going to isolate the x equals y plus 1, and substitute that into the first equation. Because if I substitute that into the first equation, I'll end up with an equation just with y. And there's no reason I can't solve for y before I solve for x. So I have x squared in the first equation, which is now going to be y plus 1 all squared, plus y squared equals 25. Let's distribute that out and simplify. So I get y squared plus 2y plus 1 plus y squared equals 25, which is 2y squared plus 2y minus 24 equals 0. I can divide out the common factor of 2, and if I divide both sides of this equation by 2, I get y squared plus y minus 12 equals 0 divided by 2, which is still 0. You don't have to do that, but it does make this factoring step easier because now I can see much quicker that the factors have to be y plus 4 and y minus 3, which gives me a y value of -4 and a y value of 3. I could substitute these into the first equation to find x, but again, I'd have to think about the plus minus, and they won't both work. It's going to be plus or minus, and how do I know which is which? Well, the second equation is much more straightforward. In the second equation, I've already solved it for x. X equals y plus 1. So -4 plus 1 is -3, and 3 plus 1 is 4. So that means my points of intersection, now be careful that you get the coordinates in the right order because I didn't find them in this order. The point is -3, -4, or 4, 3. These do work in the first equation. -3 squared plus -4 squared is 9 plus 16, which is 25. And 4 squared plus 3 squared, 16 plus 9, still 25. Graphically, we can see these 2 points of intersection. And again, thinking of intersections between a circle and a line, you could have 0 points of intersection. You could have a single point of intersection, but most commonly you're going to see 2. It doesn't quite look like a circle here because my scale is squished vertically. It looks a little more oval, but it is a proper circle. It's just that the vertical scale and the horizontal scale are slightly different, but there are my two intersection points. All right, so for exercises to practice this, in your textbook, lessons 8.1 and 8.2 involve nonlinear systems, solving them graphically as well as solving them algebraically. And there is a worksheet available in D2L with a whole bunch of systems questions in it.